Welcome to iTech Code. Today we'll be talking about our continuation on the basics of reservoir engineering. In our subsequent previous edition, we have considered the porosity of the reservoir rock. We looked at its permeability. We talked about saturation. But for today, we'll be looking at the capacity of flow. Capacity of flow for a reservoir, which gives us the permeability K multiplied by the reservoir thickness H. Permeability is in millidarcy, and your thickness is in feet or acre feet, as the case may be. The capacity flow is very critical for us to know if this fluid is actually flowing through the reservoir rocks. And if we establish this, we're going to look at another critical property, which is the transmissibility. The transmissibility of the reservoir fluid. If it is flowing, is it transmissible from one point to the other? And for us to determine that, we use the formula, our K, which stands for permeability, and the reservoir thickness over the viscosity. Viscosity which tells us the resistance of flow in this fluid. When we establish the transmissibility of the reservoir, we will be able to know how the fluid is moving from one point to the other within the reservoir space. All this will help us to determine our conductivity and resistivity. When we talk of conductivity and resistivity, we are looking at the ability of the reservoir to conduct heat or electricity within that reservoir itself. And for our oil and gas, we know it is usually non-conductive, and non-conductive fluids in the sense that it does not allow the passage of electricity through it. And our water, which the aquifer water, which most times have high salt content or ionic salt content, and if this is the case, it is usually conductive to electricity. With this, we need it to be able to determine our log analysis, where we determine the points at which we can find the gas, oil, and water profile. And when we do that using our resistivity log, matching it together with what we have in our lithology logs, we can be able to get a good profile of our reservoir for prediction and for other reservoir engineering inputs. And so, how do we determine our conductivity? We use the formula that resistivity, capital R, is equal to the resistance, small r, times R, surface area of the rock, and the length of the particular rock. So if we have this as our rock, if this is our rock, we are saying the resistance R of the rock over the entire surface area of this rock, 2 pi r, and our length from this point to this point, the length of the rock. Okay, so our big R resistivity is this value. From here, we get to know that our formation resistivity factor is equal to our resistance of the non-conductive phase over the resistance of the conductive phase. Recall, we have mentioned that the oil and the gas are usually resistive to electric currents, and the water is conductive, especially with water with high ionic concentration of salt is conductive to electricity. Therefore, we have that our formation resistivity factor is the resistivity of the non-conductive phase over the resistivity of the conductive phase. We can also equate our formation resistivity factor as the porosity raised to the power of the cementation factor M. The formation resistivity factor is also equated to our porosity over the negative power of the cementation factor M. We can therefore take equation, let's call this equation 1, and this we call it equation 2. Since we have formation resistivity in both cases, we can take the values of formation resistivity, giving us that our resistivity of the non-conductive phase over resistivity of the conductive phase is equal to our porosity over the negative power of the cementation factor. This value, many researchers, especially Archie, in 1942 thereabout, was able to establish this value using our various resistivity law. For more on the basis of reservoir engineering, keep a date with us, and peradventure you have not liked or subscribed to our channel, please do so, and we hope to meet you up in the next edition. Ciao!